Okay, so here are our list of natural deduction exercises. We're going to try to go through them together. And here are our list of inference rules for natural deduction from the book, and our list of replacement rules. So we'll go back and forth between the problem and the rules as we try to work out the solution to the problem. And here are 3 randomly chosen selections from those exercises. So we'll start with this one, right? Number 4 up here. It says if A then B, not A. Those are our 2 premises.
Does it say not A?
Huh?
It says A.
Yeah, I'm sorry, A. Right. If A then B, then A. And we are supposed to prove A and B. Yeah. So how are we going to go about doing that? First, what I'm going to do is try to move the conclusion out here so that we don't get confused. This is something separate we're going to try to prove, right? And in order to do that, of course, we have to start a new line, yeah, and try to derive from the premises that we have and the rules that we have something which will lead us to or give us a step to arriving at A and B. So what will it be? What will we put in there?
Well, there's the conjunction rule. That's
okay. What's conjunction do? Let's go to the rules. Conjunction. If I know P and if I know Q, then I can put those together and derive another line which will say P and Q. Right? So here, I guess what's going on, we have A, right? So we don't have any B though, do we? So we can't, there's nothing there we can do a conjunction with. If we had B, we could use conjunction and get A and B, but we don't have B. So first we have to get B.
Okay.
How will we get B?
Should we look over at the, what's it called, replacement rule?
Okay, is there a replacement rule that's going to do that for us? Let's go back because this is from the previous chapter, and that's why you have to really have been familiar with what we already had done to start doing this. This should be really familiar. If A, then B, A, therefore what?
Therefore B. It's like the first one. Isn't it MP?
Exactly. That's modus ponens, right? So that's not a replacement rule. That's an inference rule.
Yeah.
Modus ponens is up here. And we will write, yeah, so it'll be MP. Yeah, that's check again just to do the obvious, to be clear, right? The form is if P then Q, P therefore Q, right? Over here we have premises of that form. If A then B, A therefore B, right? And then we're going to write inside there modus ponens 1, 2. Right? Okay. And now what?
Now I think we can just go ahead and write A and B.
That's correct. Right. Maybe I shouldn't put space because that's consistent. Okay. And what are we going to put in our parentheses?
CN.
Conjunction.
Will be 2?
Right. 3. That's right. And that one's done. We got A and B. We look through. Let's go check conjunction rule again. That's right. P, Q, P, and Q. Right? So we do have premises of that form. We have A, B, so that we can get A and B from conjunction. So that's a lot of fun, isn't it? Let's give ourselves some space. It'll get more fun, Shelf.
Okay.
So we'll do number 5.
Okay.
I'm going to stretch that out a bit too so that we can, right, remove. Oops. There we go. All right. Now, we have if x then z or y, and we have not z and not y. And we're going to try to prove, or we're supposed to prove not x or a. This one's a little bit more complicated.
Mm-hmm.
Okay, one of the things to do when you do this is to look at the conclusion and look at the nature of the conclusion, right?
Uh-huh.
One of that we should notice that in the conclusion we have a variable a, which is not in the premises, right?
Mm-hmm.
There's a proposition that we don't find in our premises, a, right? And remember, there's only one rule that can get us a proposition which is not at all in the premises. Right? All the other rules that we have just give us, something which we already find in the premises, in a sense, right? So, for example, this is if P then Q. It doesn't tell us that Q is true, but it tells us there's a relationship between P and Q. And the inference rules allow us to then conclude things, on the basis of relationships that we know they already have to things that we know to be true. Okay? So in all these inference rules, the conclusion will appear somewhere in the premises. Right? It won't be asserted as true in the premises, but it will appear somewhere in the premises. Okay? And the replacement rules, because the replacement rules just tell us what are different ways we can use to express the same proposition, right? And so there's nothing that's going to be in one that's not in the other, because these are equivalent, right? There was only one rule that we have in the inference rules that allows us to introduce a completely new proposition into the mix. And that's the addition rule, right? See right here? We have P. If we have P, then we can infer that P or Q, right? With the disjunction. Because why? Well, because this isn't asserting that Q is true. Since we already know that P is true, then we can repeat ourselves essentially saying that P is true and then also saying or Q. Because the disjunction is true, right? As long as either one or the other. There only has to be one of the two disjuncts true in order for the entire disjunction to be true. So since that's the case, we already know with P, we can just bring Q in by putting or Q. Okay?
Okay.
So if we go back to our problem here, see that we have not X or A. So this conclusion isn't asserting that A is true. And we would not be able to do that with deductive logic. We would not be able to assert that A is true unless A actually appeared somewhere in the premises where we know that it has a logical relationship to something that we do know is true. But that's not the case. It's not there. So, and then that's why this conclusion, if it were just to say A, there's no way that you could actually prove A based on these premises because A doesn't appear in the premises at all. But it doesn't actually assert A. It says not Q or A, right? Which means that in order to actually get this, we'll have to prove that not Q. Once we prove that not Q, we can use addition to just, plug in the A, right? Because not Q will having the position of P here, and according to the addition rule, then we can use the disjunction and attach A to not Q by this disjunction, right?
Mm-hmm.
You follow me?
Yeah.
And so that tells us that, oh, well, we know that at the end we're going to use addition to get this. But in order to be able to use that, we have to get not X from what we have here. So that's our next order of business, right? How can we prove not X? Now I'm going to let you take it.
Okay, it's the implication form from the replacement form. Wait, is it the implication? Or the, no, transposition?
Okay, transposition is a replacement rule, right?
Mm-hmm.
So we're going to get if not Q, then not P, right? So from that, we're going to get what? If not Z or Y, then not X.
Mm-hmm.
That's not going to give us not X, is it?
Yeah, not on its own. Okay.
Not on its own. So this is one way we could do it. But I think if you do transposition, you'll be taking an extra step, which is not necessary.
Mm-hmm.
So all we do with transposition is we're switching the two and then negating them.
Mm-hmm.
Yeah. Here we have not X, and we find not X here. So obviously you're right to look at the first, premise. Yeah.
Mm-hmm.
This is a conditional, and there's one argument form which allows us to negate X from this conditional. Which one is that?
Say that again.
There is one argument form based on conditionals which allows us to negate the antecedent, which in this case is X.
Is it disjunctive field difference? But that doesn't work.
No, because that's a disjunction, right? We're talking about something that's got to be based on a conditional. The disjunction is inside the parentheses here, so we can't do anything with that yet.
Mm-hmm.
If we could get this outside, we would be able to.
But it's not empty, is it? It's not empty.
It's MT, modus tollens, right? So
okay.
if we could negate the consequent, right? We can then negate X. We would get not X. So if we can get not Z or Y, then we'll be able to get not X, which is what we want now, right? So that's our next condition then, right? So, okay, let's go through this from the beginning. We know that we need to get not X or A, and the only way to do that is by addition. And in order to do that with addition, we have to prove not X first. And from our premises, the only way that we can prove not X is to prove not Z or Y by modus tollens, right? So now the next question for us is, how can we prove not Z or Y? Well, what else do we have? Now we look at our resources. Our second premise says not Z and not Y. I mean, if it's possible for us to prove not Z or Y, it would only be on the basis of the second premise, because that's the only other thing we have, right? So that means we got to look back at our rules again. Can we get not Z or Y from not Z and not Y? So look through those rules. It's going to be a replacement rule, isn't it, right? I think so.
Yeah, I think so too. The DEM rule?
Yeah, DEM rule, De Morgan's rule. De Morgan's rule. This is one of the coolest rules for me. right? So look what we can do. Here it says, not P or Q is equivalent to not P and not Q. So if we have one, we can take the other. Yeah, and vice versa. If we have the other, we can take this one. Yeah. So going back, we have not Z and not Y. So by De Morgan's, we should be able to get not Z or Y. Yeah.
Mm-hmm.
All
Yeah.
right. So now I got to do the technical thing for you for Microsoft Word. How do you get these little symbols? If you don't know already, right, you just go to Insert. And well, since I've already been using them, it shows you the ones that you've used a lot, right? Yeah, okay. It'll give you the whole bunch of symbols. Yeah.
Mm-hmm.
And you have to just look through and find, right, here are the ones that I've already used, but they're up here. I think the squiggly line is up above there. But once you find it and you use it, it'll show you. And you can just go like this, insert. So this is an easy way to do your, right, homework, right? If you're going to print it. Well, it's not an easy way, but it's the way, the only way to get these symbols, yeah?
Mm-hmm.
And you're going to do it like this, right? Not Z or Y. And that was from DM, right? Oh, you're going to do it like this. 1 and 2, right?
So you mean,
Okay. And now what are we going to do?
does this look? Okay, I'm slightly confused about right now.
Oh, what we just did?
Yeah.
Okay,
I get
so
the DM rule. Is that how it's applied?
okay, so the DM rule, yeah, tells us two things, right? It tells us that this not P or Q is equivalent to not P and not Q.
Okay.
Right? What that means is that if we have a statement of this form, not P or Q, then we can convert it to this form, not P and not Q. Or conversely, if we have a statement of the form not P and not Q, we can convert it to this form, not P or Q. Yeah?
Yeah.
Okay, to put it in plain English, or somewhat plain English, right? If I say, I had neither coffee nor tea, what does that mean? That means I did not have coffee and I did not have tea, right? They're the same. Likewise, right? If I say, I did not have coffee and tea, that's the same as saying I did not have coffee or I did not have tea, right? I didn't have both. That means that either I didn't have one or I didn't have the other. Yeah, at least. I could have had neither, right? That's consistent with this, right? Not P or not Q is consistent with not P or Q, but it doesn't entail that, right? Not P or not Q might be true if, for example, Q is true, but P is not. Okay? In any case, that's just an aside to make sure we're clear on everything. These are the two things you can do with De Morgan's rule.
Yeah.
So, what did we do? How did we use that rule? Go back to our problem. We had, right, a statement of the form not P and not Q, right? So we used De Morgan's rule to convert it to not Z or Y, right? Because these are equivalent. Okay. And the reason we did that is because we knew that if we can deny Z or Y, by modus tollens, we can deny X, which we want to do in order to use addition to get A, to get not X or A, right? So that means our next line is going to be what?
deny x.
Yeah. And it's going to be by modus tollens from what?
2 and 3.
2 and 3?
Wait. It's 3.
Not just 3.
1 and 3.
1 and 3. Exactly, right? Because those are the two premises that we need, right? If x, then z or y. Not z or y, therefore not x. Right?
Right.
Okay. All right. We got one more step left. Do you remember what it is?
To add the a somehow.
Right. So what are we going to do? Right?
Just add the a.
And what's the rule?
Addition. AD.
AD. From 4. That's all, right?
Right.
Okay, let's just check that to review. Let's go back to our rules. The rule for addition tells us, right? If we have P, then we can get P or Q. Right? So here in the example, right, C and B. If we know C and B, then we could get C and B or A. And we would be deriving that from that very premise that we had C or B in. In that case, here, it's the premise 4, because that's where not X is. Since we had not X, we can get not X or A. So finish that one. How is it for you? Pretty clear?
Much clearer now.
Okay. All right, now let's bring this one up and get it ready. It's kind of fun, actually. I mean, I think it's kind of fun. Could get boring if you have to do it a lot, right? Actually, it doesn't get boring as long as you just keep making it more and more complicated as you go, because then there's all the time a new challenge, right? And truthfully, it can get so complicated that it doesn't really have much practical application in, your real life thinking. But it has applications in technical things. So when you get to another step in logic, predicate calculus, right? And then it has applications in computer engineering and so forth. Yeah. They actually use logic to develop computer programming. But we only want to use this exercise in logic to sharpen our own critical thinking skills, not to build our replacements. Right?
Right.
So here we go. We're supposed to arrive at y and z or y and a. So we know that we want to arrive at a disjunction, right? So basically, we always look at the nature of the conclusion that we're trying to prove to get a clue as to how we're going to eventually arrive at that, right? Because if you look at the rules, we can see that there are some rules that actually allow us to generate disjunctions. One was addition, as we just saw, right? But in this case, there's no totally new proposition, right? Y and Z and A are all already in the premises. So it doesn't look like we're going to need addition, right?
Right.
It looks like it's going to be something else. So let's take a look again at what we have here. We have a disjunction between two conjunctions. Y and Z or Y and A. It looks like that's telling us that one way or another Y is going to be true, right? Yeah. It's like saying either I had coffee and cake or I had coffee and pie, right? That's basically entails that.
Coffee?
Huh? Well, okay, coffee will be Y, right?
Uh-huh.
Because Y is in both conjunctions. right?
Oh, yeah. Okay. Right.
So, like, let's say Y is I had coffee, and
Mm-hmm.
Z is I had cake, and A is I had pie, right? So
Mm-hmm.
this is telling us, this is saying either I had coffee and cake or I had coffee and pie, which essentially means either I had coffee or I had coffee, right? That's one thing that comes out of that, which means, I had coffee. Yeah.
Mm-hmm.
So
Right.
the other is that I either had, you know, cake or pie, Z or A.
Mm-hmm.
So if we somehow can prove that Y is the case, and then also
Mm-hmm.
prove that either Z or A, right?
Mm-hmm.
Then we would be able to get this. That's just a way of thinking about it in terms of common sense. So there's got to be a
Mm-hmm.
rule that shows us how, if we had Y, and if we had also, on the other hand, Z or A, we could get Y and Z or Y and A.
Mm-hmm.
So let's look back at our replacement rules, see if we have anything like that. And it does, right? We have that. P and Q or P and R. This is the real distribution. If I have P and Q or R, that's equivalent to P and Q or P and R, right?
Mm-hmm.
Also the reverse. So I know that if I can get this somehow, I can get that. I'm not
Mm-hmm.
sure, though, that that's what I need to do in this case, but it's a clue because that's the form of this, right? So that's
Mm-hmm.
one way to get it. So that makes me ask, is there any way from these premises, is there any way that on the basis of these premises I could get Y on the one hand and
Mm-hmm.
also Z or A, right? Because that's what
Uh-huh.
P and Q or R can get me P and Q or P and R. So there's two things I'll need. I'll need P and I'll need Q or R. Okay?
Mm-hmm.
Here, that's going to be, P is going to be Y.
Mm-hmm.
Q or R is going to be Z or A.
Mm-hmm.
Yeah. So let's look at Y. Yeah. How could we possibly get Y? Well, Y is here in this conditional. If X, then Y.
Mm-hmm.
Since we know that, then we know that, hey, there's one thing that could get us Y if only we had it.
Mm-hmm.
What could get us Y? What could prove Y true?
If A was true.
A, how do you get, where does A come from?
Sorry, X.
X, there we go. Okay, so if X is true, then Y is true. And then
Mm-hmm.
we'll have half of what we need to get this thing, right?
Mm-hmm.
All right. Is there anything in our premises that can prove us that, X is true?
Um,
Is X anywhere else in the argument?
uh, where is that? 3, premise 3, X and
Premise 3. X and W, right?
mm-hmm.
So that's pretty much telling us that X is true, right? X is true and
Yeah.
W is true. So we just need to get the X out there by itself. How do we do that? Going back to our rules.
Like conjunction and reverse.
Conjunction in reverse. Well, there is a conjunction in reverse. What do we call it? Simplification. Yeah?
Yeah, right.
We could change the name to conjunction in reverse. I think that sounds cooler to me, but most of the logic books call it simplification. Mm-hmm. Okay, so let's do conjunction in reverse, or in other words, simplification. P and Q, right, gets us
Mm-hmm.
P, or it could get us Q. It doesn't matter, right? Just one of the two conjuncts we can remove, get it by itself. So we're going to take X out of there, right?
Mm-hmm.
And we're going to call it conjunction in reverse. How's that?
Better.
Now, just to be consistent, I have to say simplification. When I do my next version of the book, or the next edition, I'll change it to conjunction in reverse. And this comes from 3, right?
Mm-hmm.
Conjunction in reverse on 3. Simplification from 3. We get x. So we got part of what we need, right? And we know
Mm-hmm.
that we're going to use conjunction, right? Because now that we got x, as soon as we can get z or a somehow, some way, right? Then we're going to conjoin x and z or a, and then use the distribution rule again, right? To convert that to, yeah, what is it? X, no, y and z or y and a, right?
Mm-hmm.
Hey, that's not correct. I put the wrong one, didn't I? Catch my mistakes. We are getting y, not x.
Yeah.
Yeah, but we're not. But no. You know what? Because I'm too hasty. We have another step to do to get. So I have to remember we don't want x. What we want is y.
Mm-hmm.
So we haven't gone far enough yet, have we? Yeah, we haven't gone far enough. Now that we got x, what is it that we need? We need y.
Mm-hmm.
Yeah. Right. Okay. And how are we going to get y? That was the whole reason we got x.
P.
MP. Mm-hmm. MP. And what are our premises?
1 and 4.
Yeah. All right. Now we got y. Okay. Now we can use conjunction as soon as we get z or a, right? How can we get z or a?
C or A. Okay. W is also true.
W is also true. So we're going to do the same thing to get w, right?
Uh-huh.
Simplification from 3 again, right? Because we have x and w up here,
Uh-huh.
we took out the x with simplification. Now
Mm-hmm.
we'll take out the w with simplification. And by means of that w, we will use, right, this conditional, if w, then z or a, and we'll get what?
Z or
Z
but
or
that.
a,
Mm-hmm.
right? Okay. And it will be modus ponens 2 and what?
2 and 6.
2 and 6. Good. Okay. And then what's our next step?
Distribution.
Well, not yet. We have to get the thing we're going to use distribution for. So let's look back at distribution, right? We want to get the thing of this form, right? Y and Z or Y and A. Yeah? But what we have is Y and Z or A.
Yeah.
That's what we need in order to get that. Yeah, but we don't have that yet. So how are we going to get that? I mean, we do have Y here. We have Z or A here, but we don't have Y and Z or A the same, right? We don't have the conjunction of the two. So if we have the two separately and we want to get the conjunction of the two, which rule are we going to use?
Distribution.
Distribution. Oh, okay.
No,
Let's
no,
go
no,
back
no,
again.
no, not yet. That's the last step.
Not yet.
Yeah.
Yeah, it's the next step. Okay, so we're trying to get the thing we need in order to use distribution to arrive at our ultimate goal. And what we want is a conjunction, so right, we're going to use the rule for conjunction. Yeah, we want to conjoin y and we want with z or a. So in this case, right, y is the value for p, and the value for q is z or a. So that we're going to get y and z or a. Yeah. Y, oops, not t. Y and z or come on, get out of here. And Z or A. Right?
Right.
And this is by conjunction. From what two premises?
5 and 7.
Good. Mm-hmm. And now, our final finale. Our final finale. That's kind of redundant, isn't it?
It is.
Is there ever a non-final finale? Yeah. Does the finale ever come at the beginning? But let's do it. Our final finale.
Mm-hmm.
What is it?
It's distribution.
The conclusion, right?
Yeah.
Y, oops, Y and Z or Y and A. What's the abbreviation for distribution?
It is DI.
DI. All right, we're checking again. We had this and we're turning it into that, right? Yeah.
Mm-hmm.
Okay. Okay. There we go. So let's check that again, right? What we had is Y and Z or A, and we converted that to Y and Z or Y and A. Yeah?
Yeah.
Check if that's our rule. Y is P and Z or A, right? Converted to Y and Z or Y and A. What you have to do here is to check to make sure you did not switch any of these.
Mm-hmm.
Right? So if we're starting out in our, initial or our premise, the premise that we're working from 8, Y and Z are A, and we want to use distribution. We're saying here that Y is P, right? Z is Q, and A is R,
Mm-hmm.
right? So when we generate our new line, our new statement, we have to make sure that the values that we have set for each variable remain consistent. So that in this line, Y still is the value for P, Z is still the value for Q, and A is still the value for R, right?
Right.
Again, so here, if we're using the rule correctly, and we're applying this to Y and Z or A, right? Then we need a statement of this form. So that means our new statement has to match that form. And in order for that to be the case, the value that we set for each variable has to be the same here. So P has to be Y, Q has to be Z, and R has to be A, and it has to remain consistent. Otherwise, we messed up, right? So from Y and Z or A, we'll get Y and Z or Y and A. Yeah?
Okay.
If we put in a statement where the values of each of these variables changes, then we're going to have made a mistake. Do you understand what I mean when I say that?
Yeah.
Okay. All right. Well, we did 3 of these, and I hope that it was helpful, right?
It was.
And I hope you can go on to do the rest of them, and have a kind of a handle on how it goes. And I think once you do a few more, it should be really simple. And maybe you'll get addicted to it, and you want to do some more complicated ones. In which case, I have to dig up some from other logic books. There's a lot of more advanced logic books where they provide many really complicated problems. Yeah.
Mm-hmm.
But maybe you're not really going to like this one too much. Depends. Some people really relish it, and then other people hate it. It seems to be that's the case. Anyway, there you go. I'm glad to hear from you in class today. Hope everything goes well, and have fun on the exercises.